Hi, I'm Jessica Johanningmeyer. I'm our Quantitative Reasoning Studio Director here. I'm going to walk through some material with you from your introduction piece of the Powers of 10 and 7 brief lessons on physics, quantitative reasoning activity. So that means we're going to cover scientific notation and unit conversion. The actual introduction has material, has some explanation here. You should see that now. The bit at the beginning is about quantitative reasoning and what that is. Right after that, we see scientific notation. So there's some information here you can read through. Scientific notation is basically a way that we use a shorthand for really big or really small numbers. So instead of trying to count out and write out 11 zeros, for example, and not making any mistakes, missing any, we can use this system of writing numbers instead of the standard form. That also helps when we operate with scientific notation. We can multiply, divide really quickly, different numbers in scientific notation using the number out front and also the piece of the exponent. So let's skip down here to the example part. The first example we have here is the Big Bang occurred 13,800,000,000 years ago. And then we see what that is rewritten in scientific notation, 1.38 times 10 to the 10th. And there's a little explanation of why. So I'm going to work through that actual problem and so that we can see how that goes. So the original number that we have was 13,800,000,000. Apologies for the handwriting. I do not have a touch screen. So here's our number. In fact, just saying billion and million, we're kind of doing what scientific notation does in our everyday language. I don't say all these places. I just say 13 billion. And that means a 13 with 9 zeros after it. If I were just saying 13 billion, it tells you something, positions that number for you. All right, so one of the rules that document said about scientific notation is that we always write numbers with a single digit before the decimal place. And so in this case, my first digit in my number is a 1, so I'm going to write the 1. I have a 3 and an 8 before I get into a bunch of zeros, so I'm going to put the 3 and the 8 there. If all of these numbers were digits not 0, I wouldn't write them all out. I would round, so I still had just around 2 decimal places. In this case, since there's zeros after that, I'm going to include the 3 and the 8. So I have my first number, 1.38. And that's the same here. I can see the 1, the 3, and the 8, but I've put a decimal in after the 1. That is a rule of scientific notation. If I put 13.8, that would not be correct scientific notation. Okay, so that's a piece of it that we can almost start with. The other piece of a scientific notation number is that it says times 10 to the something. We need to figure out what that something is. So that comes from basically the difference in magnitude from our standard form number to this number out front. So from 13,800,000,000 to 1.38. How different are those? And the practical way that we do that is we count the decimal places. So in my original number, there, I didn't write it, but there would be a decimal point right here at the end on the right side. So to move this decimal from its starting point to its ending point, which is after the 1, right there, I'll make a little 1 right now. How many times do I have to move it? I move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots. The 10 is the digit in my exponent. So right now I have 1.38 times 10 to the 10th. That might be done, or it might not be. There's one more piece of the exponent that we need to think about, and that is whether it's positive or negative. So there are rules that many people learn about whether you move the decimal place to the left or to the right. I don't do it that way because I think if you forget that rule, then you're kind of out of luck. But if you understand why it's one way or the other, you can work your way through that. So what we're going to do here is we're going to think about this as a multiplication problem, which it is. I have a number which is just over 1, and I'm multiplying it by something that is 10 to the 10th. What is 10 to the 10th? Is that a really big number or is that a really small number? 10 to the 10th, 10 squared is 100. 10 to the third is 1,000. So 10 to the 10th is going to keep getting bigger by a factor of 10 every time. This is 10 times 10 times 10 times 10, and so on, till I have 10 tens. That's a huge number. Well, that's good, because 13,800,000,000 is a huge number. So 1.38, a little over 1, times a really big number is going to be a really big number that starts with a 1. That is correct. So in that case, this number is finished at 1.38 times 10 to the 10th. That is the correct version of the standard form we were given in scientific notation. Okay, let's do another example where this number up here is negative. Let's say I have a standard form number of 0.000072. Okay. In this case, if I want to put this standard form number into scientific notation, I need to start the same way I did before, with a single digit and then a decimal place and then 1 or 2 other digits. So what is the first digit I encounter here that isn't 0? It's a 7. So I'm going to write 7.2. I don't have any other numbers, so I'm just going to have a single digit right here this time. 7.2. Always I have times 10 to the something. But now what do I need to figure out? Well, in my original standard form number, the decimal place is here. The decimal is given. In the scientific notation form, it's after the 7. So I'll make a small dot there to remind myself of that. Let's see how far we traveled. 1, 2, 3, 4, 5 decimal places. In other words, I would be moving it by a factor of 10 5 times. So I'm going to put my digit in, 5, 10 to the 5th. Now if I stop and think, 10 to the 5th is a big number. It's 10 times 10 times 10 times 10 times 10. 7 times a really big number is a big number that starts with 7. That's not what I have. I have a really small number that starts with 7. So that doesn't work. That tells me my exponent must be negative. If that's good enough for you, that works. If you want to know why that's negative, we have an exponent rules. We have exponent rules, and they tell us how to work with negative exponents. And one thing that we know is a negative exponent. So I'm just going to use -2, for example, right now. I'm going to put an aside here. 10 to the -2 is the same as 1 over 10 to the positive version of the exponent. Well, 1 over 10 squared is 1 over 100, or 1/100th. You can think about it that way. So if I'm multiplying in my scientific notation number by anything with a negative exponent, I'm multiplying by a fraction where the top is 1 and the bottom is some really big number. In other words, I'm multiplying by a decimal, a very small number. In the case that we have here, it's -5, so this would actually be even smaller. It would be 1 over 10 to the 5th. 1 over 10 to the 5th is 1 over 10 times 10 times 10 times 10 times 10. It's very small. That should make sense. That is what we see here. I see a very small number that starts with 7. 7.2 times 10 to the -5th is our scientific notation value here. Let's look back at our problem sheet, our introduction sheet. We talked about Big Bang. We talked about how we move the decimal places. And we talked about a different example, but an example of if the decimal is very small. Okay, so both of these examples, and the one I did that's different, all involve moving from scientific notation, to scientific notation from standard form. You can go the other way as well. So if you go from a a scientific notation number, if I read something that says 3.4 times 10 to the third, for example, and I need to put that into standard form, I just do the same thinking, but in reverse. So I know that my number is going to have a 3 and a 4 in it. I can go ahead and start with that if I want, but I need to think about this times 10 to the third. What is 10 to the third? 10 to the third is 10 times 10 times 10. That is 1,000. So I can think about this as 3.4 times 1,000. Well, 3.4 times 1,000 is 3,400. 3 times 1,000 is 3,000. I've got the 400 on here. That makes sense. So if I'm putting 3.4 times 10 to the third into standard form, it's 3,400. A way you can do that as a shortcut, so with 10 to the third, that wasn't too bad. But if this had been 10 to the 8th, I don't know that I'd want to write out all the 10s and think about what that number is and write it out like that. So we could use a shortcut, same as we did when we put numbers into standard or into scientific notation. And that is that this 3 up here tells us how many places to move the decimal. Because this is a positive number, I know that my number, the exponent is a positive number. I know that my number is going to be large. I'm taking something bigger than 1, I'm multiplying it by a very large number, therefore I'm going to get a very large number. How many places do I move the decimal? Well, the number starts after the 3. I'm going to put a little reminder. I'll just write this out. Okay, I'm going to put a 3. I've got a light decimal. I know, like I said, I know I need a 4. I need to move the decimal 3 places. If I move left, I'm going to make a small number. I don't want that. So I need to move right. Move my decimal 1, 2, 3 spots. Put it there. Got these holes here in my number. That's a problem, but an easy one to fix. We just fill those in with zeros. So 3400 and then my decimal point. That number is 3,400. You can do the same thing. If you have a negative exponent, you just move the decimal the other way to make a small number. I hope that makes sense. Let's look back at our assignment or our introduction again. That covers all the examples here in scientific notation and should allow you to do any of the problems that you need to work with. Something that might come up that is not covered in this section here is the shortcut that I mentioned for working with numbers in scientific notation. So before I move on to unit conversion, I'm actually going to hop right back into the whiteboard and show you what I mean. Let's take our number, 3.4 times 10 to the third. And let's say for some reason I need to multiply that by 1.2 times 10 to the second. Now I could use a calculator. I could put these in standard form and multiply them out with paper and pencil. I know these exponents are not terribly large, so 3,400 times this one would be 120. I could work that out. But if these numbers were 13 and 12, this would be a problem that you'd probably want to use this little shortcut for. Remember one thing about multiplication that is helpful is that multiplication is commutative, which means I can do it then multiply the numbers in any order. So I'm going to think of this as 3.4 times 1.2 times 10 to the third times 10 squared. All I did was flip-flop these numbers to look at them in a way that I like. Multiplying 3.4 times 1.2 gives us, well, you can do that either in a calculator or in on paper. It doesn't matter. You get 4.8 if you ever have a class, if you're doing this for a situation where you aren't supposed to use a calculator or don't have one, you can work that out by hand. Does this make sense? A little over 3 times a little over 1, giving me a little over 4. That makes sense, seems reasonable. And now 10 to the third times 10 to the second. If you remember those exponent rules, You know that when you multiply two numbers with the same base, all you need to do to multiply them is add the exponents. So 3 plus 2 gives me 5. I'm going to take an aside real quick. It's not a bracket, this is an aside, and I want to show you why that works if you don't know that. 10 to the third is 10 times 10 times 10. 10 squared is 10 times 10. These two are multiplied, so I'm multiplying all these. 10 times 10 times 10 times 10 times 10 gives me 10 to the 1, 2, 3, 4, 5. So you can see that that is 10 to the 5th. If you forget that rule, you can almost work that out like that. So if I multiply these numbers, I can just quickly add the two exponents and multiply the numbers out front. For division, let's do 4.5 times 10 to the 8th divided by, let's give this a number that'll work nicely, 1.5 times 10 to the 4th. Okay, we have a number like this. In this case, the way this works to divide, I can think of, I'll draw a dotted line here, my coefficients separately from my pieces with the exponents and divide them. So 4.5 divided by 1.5 is 3. 10 to the 8th divided by 10 to the 4th is 10 to the 8 minus 4, which is the 10 to the 4th. Let's do an aside so you can see that. 10 to the 8th, 10, 3, 4, 5, 6, 7, 8. Should pick a smaller number. If I divide by 10 to the 4th, then basically I'm going to just be canceling zeros. So this 10 and this 10, this 10 and this 10, this 10 and this 10, this 10 and this 10 cancel. And that's because any number divided by itself is 1. So 10 divided by 10 is 1. Those go away. 10 divided by 10 is 1. Those go away. So 4 10s cancel out 4 of these 10s, and I'm left with 1, 2, 3, 4 10s, which is 10 to the 4th. You also could write these out in standard form and check your answer that way. I hope that makes sense. That then is the end of what I was going to say on scientific notation. So let's go ahead and move on to unit conversion. You can see here in the assignment or in the activity that a bit about unit conversion that is really used a lot. It happens when something is measured in 1 unit, but we need to use a formula that talks about that quantity in a different unit. And so we need to change the actual unit. It often has a lot in science classes, of course, but even in something like cooking. If you have a recipe that calls for something in cups, but you're either doubling the recipe or halving the recipe and you don't have a cup measure clean or handy, maybe you need to use tablespoons, maybe you need to use pints or quarts, and for the metric system as well. There are certainly lots of times when we convert units, sometimes across systems. So if you go to the doctor and you have a check and they report your weight in kilograms, that might not be meaningful to you. It comes that way out of their computer system, but you want to know what it is in pounds. You could convert units to find out. So the example here, we talked about a standard sheet of paper, which is the scientific notation example that we didn't do that you can look at on your own. And one point that that we're making here in this is that this is a really small number, 0.00005, 0.00005, meters thick. Well, a meter is a little over 3 feet, it's about 39 inches. So that's really pretty big. Why would, if in terms of measuring a piece of paper, it's not very big if it's measuring the size of a table or a room or height. But for measuring a piece of paper, that's really big. Why would I use that unit? There are lots of smaller units that would be more appropriate. And so one unit that we can use which is the one used in the example here, is called a micrometer. A micrometer is the a meter, but micro is the prefix. Millimeter would be another one that you might be more familiar with. Centimeter, you probably have certainly heard of. We don't use those a lot in U.S. education system. We use our U.S. customary units more commonly, but in science classes especially, you'll see a lot of metric units. So you might want to get familiar with those. For that reason, this table is given here. It gives you some common prefixes: tera, giga, mega, kilo. Those are all big units. Centa, milli, micro, and nano. Those are all small units. You've probably heard of nanotech. Even my 7-year-old is always telling me about nanotech. So that is probably commonly heard of. You've encountered them, but you may not know exactly how big or small they are, how they relate to the standard unit of a meter or a gram or a byte. Those are some common standard units that we use. So in this example, we go through converting from our 0.00005 meters here, and they tell you the prefix micro, which is this Greek letter mu, means that the value is 1/millionth. That's what 10 to the negative 6 is. Negative, you can see these have negative exponents for the units that I told you are small. That should make sense based on what we just talked about with scientific notation. Negative exponent means really small number. The positive exponents are large numbers. So it's 1/millionth of the original value, okay? So they already have done a job for us that I'm gonna assume that you can work through, because I skipped this one. And that is putting that number in scientific notation. So we are starting with 5.0 times 10 to the negative 5th meters, okay? And let's get the whiteboard back and clear that. So we are starting with 5.0 times 10 to the negative 5th meters. Units are really important here. And we want to change that to our new units. So here's how we do that. I'm going to rewrite it right here. Oops. Meters. When we do unit conversion, we multiply by ratios, fractions. And these are where we get our units to cancel, and we put our conversion factors in. So meters here, if this first bit were a fraction, it would be over a 1. It is not, I don't have a denominator, so it's not a fraction, but anytime you have a number just by itself, you can think of it as going over 1. That might make it a little more apparent to see that the unit meters is in the numerator. If we're trying to get rid of something using multiplication or division, what we need is for it to be in the numerator in one spot and the denominator in the other spot. Just like in the previous example where we canceled out those 10s, we did 10 over 10 and I said that's 1, so it goes away. The same thing is true with units. If I have meters in my numerator divided by meters in my denominator here, I get m over n. Anything divided by itself is 1 and therefore cancels, okay? So now my meters are canceled out. I don't have a unit, that's not good. I need to put the unit that I want in the numerator. In this case here, put my new unit in, meters are canceled, I have my correct unit, so that is good. Once my units are set, I can then put my numbers in. I always check the units first because that tells you which number to put in the numerator and which to put in the denominator. The most common mistakes that I see students make on unit conversions is to flip this conversion factor fraction. And that is because usually you read the number out of a table and you just say, oh, this many meters equals this many, whatever. And then they're backwards. We don't want that. We want the micrometers in the top, meters in the bottom. So what are these numbers? How do I know what these are? Well, if I remember, or if I look back quickly into my table of conversions or into the problem here, I see that 1 Where we go? Where did we say it? Right here. Our value is 1 millionth. Oh, here they are. They're just small. 1 micrometer is the same as 10 to the negative 6 meters. Okay, it's already set up here, matches the work we've done, or I can see it here. The multiple means that's how many meters there are, or grams, or whatever, how many of your base unit there are in one of your unit that you're looking at for the row of this table. So that's a little bit maybe not obvious from the table, but that's how we read this. Okay, so 1, let me go back to my whiteboard and we'll fill this in. 1 micrometer is 10 to the negative 6 meters. If you think about that, that should make sense. These are very small. So if I only have one of them, I don't have very much of a meter. That is very small. That should make sense. Okay. Since I have my correct unit and I have my numbers filled in, now all I have to do is actually do the math. 5.0 times 10 to the negative 5th times 1 just gives me 5.0 times 10 to the negative 5th on top. 1 times 10 to the negative 6th gives me 10 to the negative 6th on the bottom. My unit is coming along for the ride. And now I need to actually do this math. 5.0 times 10 to the negative 5th divided by 10 to the negative 6th. Well, we just talked about how to do this. There's no other number out front. So my 5.0 is going to come along. 10 to the negative 5th divided by 10 to the negative 6th. Same base, we just subtract the exponents. 10 to the negative 5th minus negative 6, write out what I'm doing. Negative 5 minus negative 6. That actually is negative 5 plus 6 because I'm subtracting a negative number. So that gives me 5.0 times 10 to the 1st. Negative 5 plus 6 is 1. 10 to the 1st is just 10. So in this case, I could just say, well, that's 50. My unit on there. You can also leave it as 5 times 10 to the 1st if you want to get practice with scientific notation. Okay. So let's make sure that matches up with what we see here, 50. And does that seem like a more reasonable unit? Well, yeah, remember we were doing that because measuring the thickness of a piece of paper with meters doesn't really make sense. And I had that tiny number. 50 is a much more reasonable number to work with. It makes more sense. It's on the correct scale. Okay, that is how we convert units. And you should now be able to work through any of these problems that require you to convert units. Just be careful to be very aware of what the unit is that you're working with. If we forget our units, that's going to cost you usually points in your work because it makes big differences in the calculations. That's really important. And I'm sure lots of professors, especially in the sciences, probably have real life terrible stories about things that happened when scientists messed up their units. So be aware of that, and please come see me or the quantitative peer consultants if you have questions as you work through these, or if you want more practice or more explanation on any of the quantitative topics that we're covering. That is all, and I appreciate you watching the video. Let me know how I can help.